So the title of this study is Outlier Detection, How to Threshold Outlier Scores, and here are the authors. Now let's start with introduction in the paper. Outliers are objects that deviate from typical data. They can represent important information or noise that harms a data analysis process. In both cases, it is desirable to detect the outliers. Now, most common methods calculate outlier score for every object, and those objects whose scores deviate too much from the norm are marked as outliers. Meaning, we calculate a range of values, and if our value is outside the range, we mark it as outlier. If it is inside the range, we mark it as a normal data. However, it is known that using simple statistics can cause false positives. Standard deviation, median absolute deviation, and interquartile range (IQR) are the most used techniques for determining the range. The problem is that the statistics used to set the thresholds are affected by the outliers themselves. To overcome this problem, the study proposes a simple but significantly more robust approach to process the data iteratively. It first applies standard techniques to remove the most obvious outliers and then repeats the same process for the processed outlier score, meaning we are doing the same thing twice. First, we detect some outliers, remove them from our data, calculate SG, MAD, IQR for the remaining data, and again calculate the range and remove more outliers. As a result, the statistics calculated after the first round suffers much less from the outliers and therefore allows detection that is more accurate in the second round. Let's talk about existing work and their limitations given in the paper. We'll start with standard deviation. This threshold technique assumes that the data follows normal distribution. It calculates the thresholds as Gmin, Tmax, where min and SG are corresponding statistics of series with outliers. Now there are three problems with SG threshold technique. First, data including outliers should follow normal distribution. Second, outliers seriously affect the mean and standard deviation. Third, there is only a small percentage of outliers, but in some cases, the amount of outliers can even be more than 50%. What it means to say is that this method takes a very small percentage as outlier. However, sometimes it may so happen that more than 50% of our data is outlier. Now, the next, median absolute deviation method. Median is the object value ranked in the middle or the or the average of the two central objects in case of even-sized dataset. In general, MAD threshold strategy calculates the threshold as follows: Tmin, Tmax, and MAD, where MAD is beta times median of absolute value of x minus median of x. Unfortunately, the MAD is also affected by outliers, especially when the amount of outliers exceeds 50%, which causes median to be located within the outlier. If the amount of outlier in our data is greater than 50%, our median will also be an outlier and subsequently affect all the processes. Now, third method, interquartile range. The quartile range is the difference between the values ranking at 25th percentile and 75th percentile in the data. The values are denoted as Q1 and Q3 respectively. In general, IQR threshold strategy calculates the thresholds as follows: Tmin, Tmax. Now these are some of the existing methods present in the study. Now we will talk about the root stage thresholding technique proposed by this study. Now since it is two stages, we will have a first and a second stage. In the first stage, the most outlying scores are excluded from the process to reduce their effect in calculation of the thresholds. So it is pretty simple. We remove some of the outliers so that to calculate thresholds, when we are calculating thresholds for the second stage, our calculation will be less affected by outliers. In the second stage, any standard threshold can be applied using remaining scores. The purpose of the first stage scaling step is to make the second stage threshold calculation more robust in the presence of very noisy data points. I think it's clear. There are two ways to decide which outliers are removed. First way, for the first step, there are two ways in which we remove outliers. First way is to remove the biggest outlier scores manually using domain-specific knowledge by the researchers. So the researcher has some domain-specific knowledge and he may be capable of removing the biggest outliers manually. However, this can be time-consuming, especially in case of big data. Second way is to calculate the threshold using MASD, MAD, or IQR and then remove the objects whose score exceed the threshold. So either we can, for the first step, either we can remove manually or calculate thresholds, remove outliers, and then for the second stage, we will recalculate the threshold values via SD, MAD, or IQR again over the remaining scores. However, if outliers are neatly removed at the first step, duty can fail by inadvertently removing inners. Instead of outliers, we will be removing required data in the second stage if the amount of outlier is very small. Therefore, duty can improve when the data has a lot of outliers. Now, the researchers have done some experiments using 2T and our traditional method to prove its effectiveness. Let's look at that. So, to study the performance of 2T, the study tested 2T with both manually generated outlier scores and outlier scores produced by outlier scores in real-world datasets. The study first tested the manually generated outlier scores listed in Table 1, which have varying number of outliers and outlier score. The study evaluated the results with F1 score, which is average of precision and recall. So, what basically I am saying is that for study tested with both manually generated and real-world dataset. For manually generated dataset, manual generated dataset is given in Table 1. We have X0 to X4. We have inners and different number of outliers. Note that in X1 we have 1, in X2 we have 2, X3 we have 3, and in X4 we have 5 outliers. So if you look at Table 2, it represents data from X0 and we didn't have any outlier. None of the methods detected any data as an outliers. Now also notice that we have added outliers on the right side. I mean to say greater than numbers on the right side. So we can only calculate T max to separate the outliers. We have not added any outlier on the lower side, so we wanted to calculate T min. So for X0, the thresholds didn't mark any data as outlier, which is good. Now for X1, we have one outlier, but SD didn't detect any, while MAD and IQR methods detected the one outlier. For X2, we had two outliers, 500 and 1000, SD couldn't detect any, MAT detected both of them, IQR detected only one. For X3, we had two outliers, 60 and 1000. All of them detected 1000 as an outlier, but only IQR detected 60 as an outlier. For X4, we had 5 outliers, 60, 300, 500, 1000, 1500. None of the method detected all of the outliers, but clearly MAD performed better than the other two. So for calculating thresholds, these thresholds we had used A equals to 3, B equals to 1.4826 and C equals to 1.5 in the Tmin and Tmax formula we had. Now we will use the proposed 2T to calculate the threshold in order to check its performance. We have used the same value of A and C. The obtained threshold values are shown in table 7. You can see that 2T, MAD and IQR succeeded in all cases X0, X1, X2, X3 and X4, whereas ST succeeded in X0 but fails in the rest. So these thresholds calculated with the help of 2T, these thresholds calculated with the help of 2T are capable at detecting all the outliers in X1, X2, X3 and X4 using IQR and MAD methods. ST method has failed to detect the outliers even with 2T, except for X0 when we have no outlier. So what is the gist is that SD failed to detect outliers for X1, X2, X3 and X4 even by calculated new threshold using 2T, while other methods detected all the outliers. Now, as we have all of A, B and C as parameters that we can tune, we try to tune, we will check if their tuning can help improve our results. So if you remember, I just said that SD failed in all cases to detect outliers, right? We had A equals to 3, B equals to 1.4826, C equals to 1.5. But now we will change A from 2 to 5 and we will put C equals to A by 2. And we will calculate thresholds for X4 only, right? Where SD had failed initially. Now as we change A from 2 to 5, you will notice that SD was actually able to detect all the outliers for A equals to 2. Initially we had A equals to 3 and SD failed to detect any outlier, but when we changed A to 2 and C equals to A by 2, SD was able to detect all the outliers, and so were other methods. So what it aims to prove is that parameter tuning can be helpful to get better results. Now we have seen the results for manually generated data. Now for real world data, what the study did was it used A equals to 1, and for each data set here, these are the real world data sets. These are the size, number of rows, these are the number of outliers, these are the number of dimensions, and this is the feature they are checking for outlier. What they did was that they used the original data for the original data with two machine learning algorithms, MOD and KNN, and original data, without outliers detection and removal. And for this is the average F1 score for all the data sets they tested. This is the average F1 score for the data they use 2T with standard deviation, and this is the clever standard deviation, but you can ignore this for now. Understand that F1 score, the greater the better, and the 2T help to improve the overall prediction accuracy in average in the data sets. Right? Similar results can be seen for MAD and IQR with MOD detector algorithm. With KNN also, it has improved the average F1 score. Here it is slightly decreased, but about the same. Here it has again improved. So coming to the conclusion, in this paper a new two-stage thresholding for outlier detection is proposed. Experimental observations according to this study have shown that you are first excluding the scores that exceed the original threshold values and then recalculating the statistics. The actual outlier removal process can be better. So it wants to say that we have to repeat the process twice to detect more outliers in a data set which has a lot of outliers. That's the end. Thank you.